with our expression, that is, okay, we can do it in two different ways. So let me do it in the following way. You start with exponential minus of some jx mxy. So I will even cut it down further. It is j mj. So this can be j transpose mj. This quantity can be Fourier transformed with a minus I phi j. This is what we did, and then we did an integral over all j's. This is a formal integral over all j's. So we started with our vacuum to vacuum amplitude, which was expressible in this form. Then we did a Fourier transform of that, introducing a set of conjugate variables phi with a e to the minus I phi j. Then we found that this result can be expressed in the form some g0, which we promised we will come back to, times e to the I times what we call the action for this phi. Okay? And this g0 actually was determinant of m to the minus half, which we have to stare at today. So let me write it down here. But before I do that, I want to write these things down in a slightly more formal way, because this is a very standard result in field theory and it will be repeatedly used. The way you will find field theory books describing it is that they will usually describe it in the reverse direction. They will say that integral, let me write it down and then explain, some d phi, the exponential of the action plus I integral phi j dx or d4x. This is the quantity which, this is just that part, so it will be determinant of m to the power plus half e to the minus half this integral dx dy g m g. So let us try to understand this a little bit. We originally had a Fourier transform like this, and then we found this action. Then I can do an inverse Fourier transform of that, which is what I have done here. When I do that, I will just pick up this part, which is what I have written down here. Okay? Now, when I am doing the inverse Fourier transform, let us look at the structure of A once again. This came from something like minus half this I times A, so to speak, integral dx dy, or even just dx will do here, phi, some operator d phi. Remember, we worked it out. We worked out an operator d, which was an inverse of this m, the matrix m, and then that turned out to be box plus m square minus I epsilon. Then we converted that box plus m square minus I epsilon into, by integration by parts, into some phi I, and that is how we got this action. Okay? So d and m are inverses of each other. Therefore, I can also write this result as determinant of d to the minus half, and this m as d inverse. This is the way you will usually find the result quoted. That is, you start with an exponential. They may put an I here, they may not put an I here in most of the textbooks, either because it is working in Euclidean or because I is absorbed into t. That really doesn't make much of a difference. So you have an exponential of a quadratic functional with an operator sitting in the middle. Just to make it absolutely certain, let me put a d here. If you do a Fourier transform of that quadratic functional, what you get is another quadratic functional with the inverse of this d coming in here. So most of the time what one would be interested in doing in field theory is to find the inverse of an operator. So I want to spend a little bit of time on that formal structure of such an operation. So you have d and you have a d inverse, and d, we originally started with d inverse and found d, but you may also want to do it the other way around. The procedure remains exactly the same. What is involved in both these calculations is that you had an I over p square minus m square plus I epsilon. You multiply this by minus I into p square minus m square plus I epsilon, and you get 1. Okay. This quantity is the inverse of the propagator, and that propagator is what sits here because it came from this. This m was x what? Remember? This quantity is our original x y, whose Fourier space structure had this. The Fourier transform of this was giving you this. Therefore, this is what we have been calling as m in the Fourier space. This is m of p. The inverse of that is what we have written down here. This is d of p. It may not look much of an operator until you realize that this d of p is supposed to be multiplied by e to the ipx and integrated. Then this p square becomes minus box. Okay? So the operator form of this relation is that I can take this to this side and keep this on that side, that is instead of multiplying it here. So if I do that, I get your minus I, this p square becomes minus box, therefore that minus sign goes away, so I get I box plus m square minus I epsilon, this quantity multiplying this. But now I have already made it into some x dependent object, so this should be in the Fourier space. But that is nothing but x, y. Right hand side 1 should be replaced by delta of x minus 1. Okay. I mean, all of them look simple, but they are at some level quite important relationships. This is something which I have thrown in an exercise for you to prove. Okay. So what it is telling you is that here is an operator. This is your d of x. It's an operator acting on your m of x comma y, giving you this delta function. So this is again something into something, being these two acting as inverses of each other. This you should be absolutely comfortable with, and you should actually know it by heart, that whenever you have a quadratic operator like this and you do a Fourier transform, you end up getting another quadratic object there with the inverse of this object. And the prefactor will always be the determinant of either one of them. The place where you are integrating, it will come with a minus sign. That is, if when you are doing this integral, if there is an operator sitting here, it will come with a minus half of that operator. But that is no more complicated than the mnemonic is to remember the Gaussian integral. E to the minus ax square, if you integrate, you will get root pi by a. So it is a to the minus half. That a gets replaced by this because essentially when you are converting it using the operator, you are taking the eigenvalues and you are doing the quadratic integral on each of the eigenvalues, and that will essentially give you the determinant to the minus 1. This is what is happening. Okay? Fine. So if you have some structure like this, I can do this Fourier transform and obtain this structure where I end up getting something like the action. And we by now know that the action can be written either in a form with this quantity, with a phi at the left and phi at the right as a quadratic object, or this box can be integrated by part to get you a quadratic term like di5, di5. Both of them are equivalent as long as the surface terms can be ignored, which you can do for everything except probably gravity. So it is alright. Now we want to go a little bit further because we are going to now, first I want to spend some time on this determinant because we have done this in a very rapid way earlier on and I want to do this more formally. Then we are going to stare at this action itself. But before I do either of them, you can see that if you forget where all these came from and look at it purely formally, this can be done for a much wider class of structures. Just to give you an example, here your J was a scalar, right? But suppose J is a vector. Then what would happen here is that this is of course a shorthand notation for just the xy. In toto, it is going to look like integral dx, dy, j at x, some m at x minus y, j at y. This is when j is a scalar. Suppose j is a vector, you add a vector index here, ja, jb and an ma. You can have something like this. So instead of thinking of a scalar source, you are thinking in terms of a vector source and you are asking how will the vacuum be modified or disturbed by the presence of a vectorial source. In principle, one can study that. Exactly the way we have studied your original scalar object. So now you will say that it is going to create particles and destroy particles which are vectorial in nature. And the corresponding field, when you want to do this Fourier transform, should go to, it should get added or when you are doing the Fourier transform, this should have a canonical object which will go as phi a of x, j of x. This is a vector, so maybe I should write v. Okay, so you instead of the scalar field, I could have done a vector field here, and everything will go through exactly in the same way. What will happen here? You will end up getting an action. It will have a quadratic form. And this particular operator which I have written down will become more complicated. Depending on what is MAB XY is, you will have the inverse of that. So now you have to invert not only on X and Y, which will make it an operator, you also have to invert the matrix on the indices A and B. So that will add two indices to this D of XY here. Okay. So you will end up getting an action which will have a structure like integral dx, some VA, DAB as an operator acting on B. We will do examples of this later on, but I am just trying to tell you is that there is, once you have done scalar, you have done everything. I mean, it is just more complicated notation and keeping track of all the indices, etc., etc. Okay. There are some issues depending on the nature of the vector field. There are some issues about physical degrees of freedom, etc., which we will come to when we do electromagnetism. But formally, this structure can be extended to anything you want. You can have a second rank symmetric JAD and then study what is its canonical field is. Okay. So this is a very general way of looking at things. You start from there and you do its Fourier transform and you obtain this. Okay. Now let us go and look at this determinant of d to the minus half a little bit more carefully. Now d is an operator. So the question is, how do you define determinant of an operator? Okay. That requires some formal machinery which I will try to set up. There are several ways of doing this. Whenever you are dealing with matrices and functions of matrices, there are several ways of defining these quantities. The simplest way, well, simplest in conceptually, but algebraically that is not usually the simplest, is to think in terms of eigenvalues. So if I have an operator D, think of D Fn equals lambda n Fn. There is an eigenvalue equation for that operator. Then you find all the eigenvalues. So you think of the determinant as the product of the eigenvalues. Okay, and this is assumed that there is some way in which you can take limits and infinite products can be computed, etc., etc. If you can do that, that is one way of doing this. The other way is to work in momentum space, at least for the kind of structures which we are working in, where these operators essentially depend on x minus y, because your original matrix which you started with, the propagator or the green function depended only on x minus y. Therefore, the operator which comes in will also depend on only x minus y. For such objects, there is a nicer way of doing this using Fourier space. So I want to illustrate that concept first, and then we will use that to evaluate this quantity. And when we evaluate it, we will find that it is physically a very interesting object. Okay, so to do that, I want to understand how do I define functions of, let us say, matrices f of m, where m is a matrix. The way it is done is that you first look at the function. Suppose there is an f of x which has a power series expansion Cn x to the power n. Okay. Now I am assuming that it has a power series expansion around x is equal to 0. We will very soon work with the log of a matrix where you don't have a power series expansion around 0, but that really doesn't matter. The point is that either you can write a logarithm in an integral representation where that quantity has a power series expansion, or more simply, if m has a power series expansion about 1, let us say, which log a has, you write this as m plus 1 minus 1. So you keep that 1 and then m minus 1 you call it a new matrix. Work everything out with that new matrix and convert it back. So it really doesn't matter. Virtually anything which we want to work with will satisfy this criteria. If this is true, then f of m by definition is summation over n Cn m to the power n. Okay, so m to the power n is the standard matrix multiplication of n of them, and then you sum it up, and that is how you are defining it. So what we need to understand is how do I give meaning to objects like m to the power n in Fourier space. Now, the matrices which we will be dealing with, I told you that it will only depend on x minus y. So it's a matrix with two indices x and y, but the quantities depend only on x minus y because we start from a continuum object, right? So the way one would work with it is that let us consider m of x minus y and write it as integral m of p e to the minus ip x minus y. Let us work in 4 dimension. It generalizes to any dimension upon 2 pi to the power 4. So this is your m. Now I want to look at the object m to the power n. What is m to the power n? Let us write it down. So I have m to the power n of x minus y. I just have to keep combinatorics right, that is all. So I am going to multiply n copies of this quantity. Okay? So it's a good idea to introduce P1, P2, P3 up to Pn. So we will do that. So I am going to have integral over dpi d4pi upon 2 pi to the power 4 for each one of them. And I want n copies of this, so each one of them will have a p. So I goes from 1 to n copy. That takes care of the integral. Then I am going to have m of p1, p2 up to m of pn. That is fine. Then each one of them will come with a e to the minus I p1. Now we have to be a bit careful. So what does that product mean? The product means that you start at the left end, which is, these are indices. Think of it as mxy. Then the next one will be my something else, etc., etc. Okay? So essentially what I am going to have is, there is a p1 which will multiply, let us say x minus, let us introduce some variable, z1. Then you will have another one which is e to the minus I p2 z1 minus z2, etc., etc. So what will the last one have? The last one I want to have y. Okay? So I will have e to the minus I Pn. I want to put y here. So I want to know what this is. This is going to be, if this is P2, it is 1 less than that. Right? P3 will come with Z2. So Pn will come with Z to the power n minus 1. Okay? Hopefully the combinatorics is right. I mean, anyway, we know the final answer. So this is just to give you formally how it is working out. So you have got up to this.
Sir?
Yeah.
Sir, is this, I mean, are we doing a path integral?
No. We are just doing matrix multiplication. What we are doing is, okay, let me just complete this and then I will come back to that. Then because it is a matrix multiplication, there is summation over these indices which I have to introduce. So I have a whole lot of integrations over dz1, dz2, etc. all the way up to dzn minus 1. Okay, since people might have got lost, let me explain what we are doing. What we are doing is that this, you think of it as a matrix mx1. This is given to you. Okay? Now I want to take nth power of that. How do I take the nth power of that? Suppose I want to take the cube of that. Then what I will do is to write m x, let us say z1, m z1 z2, m z2 y, and then I will sum over this z1 and then z2. Correct? Because it is just matrix multiplication with indices. That is exactly what we are doing, except that my indices are continuum. So each one of them I am doing it in the Fourier space. The summation over all these intermediate things in an index becomes these integrals. Then the matrix itself is written in a Fourier space, therefore there are these p's. That's all. Now all these things will immediately telescope down to a very simple expression. So the trick is that you do all the z integrals. So when you do dz1 integral, what will happen? These two will combine together and it will give you a Dirac-Delta function on this p1 minus p2. Similarly for all of them. Then you do all those p integrals. So everything will go away and you will be left with just this x and that last y with one p, and all these p's will be equal to that p. So just work this out for yourself and you will find that this is going to be equal to d4p upon 2 pi to the power 4 m of p to the power n e to the minus ip x minus 1. Okay. Once you have the result, it is fairly easy to understand intuitively. If you have thought of this as, for example, diagonal matrix, then when you take, if you have a diagonal matrix with eigenvalues on the diagonal, if you take the nth power of that, it just picks up the nth power of each of the eigenvalues. So whenever you do any function, it will just carry through and the form of the function will just get translated into the other space, which is exactly what is happening. So you will have an expression like this. This in turn means that if I have some function of a matrix, because the function of the matrix is just the sum over m to the n, and m to the n we have already computed, you can immediately write this as integral d4p upon 2 pi to the power 4 f of that particular matrix in p representation. Okay, so I'll just call it f of p, because this is m to the power n, so this is some arbitrary f, so this is f of p e to the minus ip x minus. So whenever you have some kind of a matrix representation and if you want to get it x minus y, if it is a function, you just go to the Fourier space and take that function. Okay, so that is what it means. What if the matrix is from an operator? Then you have to take that operator and that operator should be sitting here. Because you, instead of, that is exactly what we did here. When we arrived at these kinds of operators, if I write this on the left hand side, I converted this p square operator to a box and then converted this into xy. So this relation, which I have written down here, and this relation, you should be comfortable in going back and forth. This is an operator acting on a function which depends on two variables giving you a Dirac delta function. The corresponding relation in the Fourier space just tells you it's a product of two numbers giving you unity. Of course, Fourier space looks easier, but most of the time we want to work in real space, so we need to deal with this. Okay? So this is what will happen whenever you have functions of matrices to deal with. Fine. Now let us get back to what we have in hand. So I'll probably need some of these. So okay, so let me just erase this. Okay, so let us look at what we have got here. We are after this determinant. Okay, so I concentrate on that relation. The first thing you know is that this determinant to the minus half is what you get if j is equal to 0 on both sides. Suppose I put j is equal to 0, this term will go away, only the determinant will survive. And here if I put j is equal to 0, only this will survive. So if I take an action which is of this quadratic nature, and I do this sum over all phi, which is a functional integral over all phi, which we have never bothered to define precisely, but it is just an idea that we can eventually discretize everything and work with that. So if you take that functional integral with no j, you are going to end up getting this quantity. Okay? So let me try to do this just for convenience in Euclidean space, because Euclidean space things work out nicer. What we have is an integral over d phi e to the minus half integral dx Euclidean sum phi, sum operator, sum phi. This quantity is turning out to be determinant of d to the minus half. Yeah.
Do you really mean f of mp or f of p over there?
Oh, it's a f of n. Sorry. But actually, I can do it in the following way. Suppose I have m to the power n here. Okay? So, what I am saying is that this particular quantity, suppose I think of f of n as m to the power n. Then I get m of p to the power n. Right? That is, whatever is the matrix, I rise to the power n, and that is what I am going to write this in Fourier space.
Yeah.
So in the same way, if I am going to have some other arbitrary function, I can think of it as f of p. So the notation is defined by saying that your matrix goes away. Whatever, suppose f of m was m to the power n, right? Then I would have taken an m of p n, and maybe as you say, the notation wise, it is better to call this mp.
The same f, not f twiddle or something.
F twiddle or something. It is not the same f.
That
Okay.
makes sense.
So there is a function which is involved, and then you do that. Okay, fine. Thanks. So this is what I want to do. But what I would like to, before we do the computation, I want to come back. We did this once before, but I am going to do this more formally now. I want to know what is the best way to write this. So here is an operator d which could depend on various things. In this particular case which we are studying, the operator depends only on this parameter m square. But in principle, I could have had a more complicated kinds of operators which depends on something. It also depends on this phi through this quadratic expression, and we have integrated out phi. And I also told you that whatever you get here, that is, you started with this which was thought of as a generating function, then you introduced the conjugate variable, and then you did the integral. What you get here should be thought of as a probability distribution. In the Euclidean space, that is quite a nice way to interpret the action. So this e to the minus action, we think in terms of a probability distribution. Then if I sum over all phi, that is like a partition function. Because when you have e to the minus beta ei and you sum over all e, that is what you call the partition function. And in most field theoretic lectures with Euclidean action, they will just call it the partition function of the field theory. What I mean is, this is what is being computed. So if it is a partition function, then it is much nicer to write this as e to the minus some effective action. Because there was a e to the minus this action, I have summed over and I have written it like that. This is what we do in StatMath. You take a partition function and you write it as e to the minus beta times the free energy. So essentially, this A effective is like a free energy, which you are going to compute for this system. Here this D depends on certain parameters or the background fields or whatever it may be. In this particular case, only m square. So this quantity will also depend only on that parameter. And that is what we want to know, what its dependence is. And what is the physical meaning of this quantity. So taking one step further, we can write this as e to the minus integral over again dxc, which is d4 xc of some Lagrangian, which I will again have to put LF. Because the original action was an integral over some quantity, which was a, yeah.
Can you please explain again what is the motivation for A effective?
This one. Okay, so let us go back to StatMath. I mean, at some level it is only a definition, but it's a very useful and important definition. So let us do that. So if you look at StatMath, if I have a canonical ensemble, then the partition function Z of beta would have been defined as summation over I e to the minus beta times ei. Right? This is your standard partition function. Now, this quantity by itself you can work with it and do all kinds of calculations. But whenever you do that, you will find that the log of Z is what comes in. Like for example, if I want to compute the mean energy, then I will if I differentiate this with respect to beta, I will get a ei times this, which is almost like the mean but not quite, because it has to be normalized by summation over I of this e to the minus beta I. Therefore, it is log Z's derivative with respect to beta which gives you the mean energy. So the log Z is a physically much more well motivated quantity. If there was just one energy which captures the effect of all these, suppose I want to give, this is like a sum over a whole lot of them. Think of it like an average. But suppose I just want to give you one quantity which captures the effect, then I would like to replace it by something like e to the minus beta times that energy, which happens to be called free energy, like this. This is our definition. This definition works because you have exactly this structure here. Suppose there was only one energy, then ei will be equal to f. When there are several of them, you sum it up and then you put the same structure which is appearing in the left hand side on the right hand side. That is what we are doing here also. You have different functions f of phi of x. For each one of them, action takes a particular value, and I am summing over all those forms of phi of x. Then what I get, the effective action, if you give me a single action functional which captures it, that you think of it as e to the minus a. Okay, that is the motivation. Fine. So we will write this as this quantity d4x times L effective, and we want to know what is L effective. So how do we find that out? We already know what it is. This quantity is just determinant of d to the minus half. So we just have to figure that out. So what we need to do is to take the logarithms on both sides. Then I will get minus integral d4 xe L effective is equal to log of this, which is minus half. So this half minus half log of determinant of d. Okay. Now log determinant of d is half of trace log of d. This I mentioned in a previous lecture, but this is something which you guys should be familiar with. If not, you should work it out. You should know that log of determinant of d is trace of log of d, and the easiest way to prove this is to diagonalize it and then take the eigenvalue. Determinant of d is the product of eigenvalues, so log of that is the sum over log of lambda I. Log of lambda I are the eigenvalue spectrum of log d. Sum over I becomes trace. Okay. Now we want to give meaning to this trace. So how do you give meanings to this trace? Suppose log d has been expressed in Fourier space. Okay. Then the trace would just involve the integral over all the diagonal elements. Correct? And log d does have a nice representation in Fourier space, from which you can obtain that. But you can also give it the same quantity meaning in the real space. The way you do this is to think of this trace as a d4x again. So you write it as d4 of xe half. This d4 of xe is taking care of the trace. Then you have a log d, which you think of as the matrix element x log d x. So d is some operator. Now we are thinking of it as acting on the x space on a space of states like this. Okay. This is just our normal quantum mechanics. In fact, in Euclidean it is nothing more than quantum. Here it is, you have already got this d4x taken care of, and it is also usually nice to write this log d as integral 0 to infinity ds over s x e to the minus sd x with a minus sign. So this also I showed you the other day. What is being done here is to write log of some quantity q as integral 0 to infinity ds over s e to the minus s cube. If you differentiate both sides, left hand side will give you 1 by q. Right hand side, when you differentiate with respect to q, it will produce a minus 1 by s. So that will be ds 0 to infinity e to the minus s cube, which is minus 1 by q. Okay. Now these manipulations are a little tricky because this integral is divergent at s is equal to 0. That is one reason. Second, it is very uncivil to write logarithm of things with dimensions, which we have been doing all along. Because if you go to momentum space, we will write it quietly as log p square plus m square. So in the back of the mind, we have some reference d naught, which we are subtracting. Okay, and it never makes any difference because after you have computed this is like dividing this by a normalization factor. Okay, so we will be a little bit cavalier about it until it comes and hits us. At that time, we will try to do this more carefully. So this is fine. So you have got this expression which gives you what it is. That allows you to identify what is L effective. So your L effective here is just this d4x goes away. It is minus half this quantity. But this is what I told you long back is a very nice object, because what is this? This can again be thought of as a propagator. What was our d? Okay, d was defined like this, so we have to track it back. So it is okay. So if I had originally written down this action, this was our d, which was the inverse of this quantity. So the d which I have has a box plus m square. So let us do that more properly. What I have is integral d4x in real space. I times integral d4x is what will sit in the exponential. I have half dA of phi minus m square phi square. This is how an action would have been given to you, some quadratic term and some other term, right? With m square always being understood as having a minus I epsilon inside it. Then what you do is that you quietly write this as dA of phi minus phi box phi. And you throw away this term. So this entire action becomes I times integral d4x, what sits in the exponent becomes half. Then I have this with my minus sign, this with minus sign, so I might have to put an overall minus sign. Then I have a 5 box plus m square 5. Okay, this is what I would have had in real time, and the real time d4x has a dt and a d3x. And when you go to the imaginary time, you change it to t. Okay? The rule for that is, if you think of a standard classical mechanics Lagrangian, it is I integral dt, then you have a half q dot square plus whatever. So if you change this I dt to dte, this will become dte. Then this is going to give you your much needed minus sign. Minus half dq by dte the whole square, because we want the overall thing to be negative. So this is the way you should be rotating, which I explained to you. It goes in the reverse and in the clockwise direction in the complex plan. Okay, so I dt has to go into dte, so this I goes away and I can call this d4x. Okay, so the d which we are talking about is essentially this quantity box plus m square. Now, one point to remember is, suppose I multiply d by 33. Okay, so I have a 33 sitting here. Now you change s to 33 times s. The integration doesn't matter. Therefore, it will come back. So the overall constant in d doesn't matter. That is because we started with log d, and there is an overall normalization which you have thrown out. Okay. So we only need to worry about this box plus m square, so to speak. But now box has to be written into Euclidean space, because we have converted this into Euclidean. So this box was originally d square by dt square minus del square. That will go over to minus d square by dt square plus del square. So this box is going to go over to minus box in the Euclidean space, right? Because there is an overall minus sign here. So the operator which we are interested in is minus box d plus m square acting on x. Fine, this is what we have. Suppose you were in 3 dimension, then this would have been minus del square. What is minus del square? Minus del square is just the Hamiltonian operator for a particle with a mass equal to half. Okay. So if, and this m square is just an additional constant potential. So this is Schrodinger quantum mechanics with a Hamiltonian for m is equal to half and v is equal to m square. What you are doing here, if this x and y were different, is just the Schrodinger free particle kernel for a particle to go from one point to another under the action of this propagator in time equal to s. Of course, we are doing things in Euclidean, but that doesn't matter. So this is just normal, honest to God quantum mechanics. It turns out that we can only solve problems in quantum mechanics. So the entire trick in good quantum field theory is to reduce quantum field theory to quantum mechanics. That is why we work with harmonic oscillators, quadratic potentials, or things of that sort. Okay. Ultimately, you have to get it back to quantum mechanics. So you have this structure, and this is x and y. If I think of it, it is a propagator. The only non-trivial thing is you are going to integrate over ds upon s. The way this has been done, and the way this is done in all textbooks, it is very difficult to understand the motivation for this 1 by s. But long back when we did this, I explained to you where this comes from. Suppose you do the whole thing in 4 dimensions. If you do it in 4 dimensions, it's again 4 dimensional. You have a propagator which is going from one point x at s is equal to 0 to another point y, which happens to be x, but let me just write this as y at s is equal to s. This is the propagator amplitude under the action of a Hamiltonian. Then if I had integrated over all ds, I would have got the Green's function xy or the propagator. But that is not what we are doing. We are dividing by an s. The reason we are dividing by an s is that you first put a e to the minus, if you have been doing it in Lorentzian, e to the minus I es, and you integrate over all s to get the amplitude for the propagator or the particle to go from one point to another with an energy E. Now if I put x is equal to y, this would correspond to a closed loop in space-time with an energy E. And the half takes care of the fact that I can have a loop like this or a loop like this. So half of it you take. And that particular quantity, if I now integrate over all energy, I get an integral over this E that brings down an 1 by s. Okay. So the reason I am mentioning this is that this is never stressed in the textbooks, because formally you get this, but what does it physically mean? What it physically means is that you have a closed loop in space-time, which are allowed for us because you can have a situation where this is space and this is time, and a particle goes around this in a proper time s, or with an energy E, which are related by a Fourier amplitudes, and there is no particle here and no particle here. So you can compute what is the amplitude for that, associate an energy with it. We did all this long back, and then you integrate out all the energy that brings down the 1 by s. So in some sense you expect this to correspond to the energy contributed by the backbone to this whole picture, and that is what we have to identify in here. So we have come up to this, and you have got this result, okay, e to the minus s times this quantity. Now it is plain sailing, because you are supposed to evaluate this, and the standard rule is I could have put a p state here and a p state here, and converted this del minus del E into the momentum representation. That would have given me a p square, and I would have done the whole calculation. So normally I would do it with a x and a y, so I will end up getting e to the ipxy, right? So what are we doing here? We have a e to the minus s times some operator or a matrix. We are converting that operator or a matrix into a p representation and then multiplying by e to the minus ipx. This is exactly what I told you, that whenever you have a function of a matrix, here the function of the matrix happens to be an exponential function. It is e to the minus s times d. Whether it's an operator or a matrix, I will use those terms interchangeably here, because you understand from the context which one I am talking. So this is what we want to do, and let us just compute this. So this is going to be minus half integral 0 to infinity ds upon s. This x and p, the moment I have introduced that, it is going to be a d4p integration, d4p over 2 pi to the power 4 e to the minus s p square plus m square. I hope you understand. I have put a p here, actually I need to put a p only here. So the moment I put a p here, this becomes plus p square, it comes out, and then I have a px, that is just 1. Yeah, sorry, you had a question?
1 by the omega p factor on
Which 1 by omega p?
we are considering the complete set.
No, this is, okay. There are two kinds of complete set of momentum space which you have to distinguish between. One of them is in three-dimensional momentum space, when you want to introduce p with a vectorial thing here, then it is very important to have d3p upon 2 pi, 2 omega p with a 2 pi etc. That is not what we are doing here. It's a good point. Here we are doing pi and xi in 4-dimensional space. There is an extra time here. So think of this as quantum mechanics in 4 plus 1 dimension. 4 space dimensions and 1 time dimension, and I want to do Schrodinger quantum mechanics. Then in 4 space dimension I can introduce the standard vectors, standard vector spaces, standard momentum, standard normalization. Nothing will go wrong. So d4p is my invariant integration. See, why did we get this 2 over omega p? Because we wanted to do an integration over d3p, but our invariance group was the Lorentz group, not the standard rotation group, and we wanted Lorentz invariance to be maintained. Therefore, you needed 1 upon 2 omega p. Here we are actually doing a 4-dimensional trace. That is, this trace is a 4-dimensional. You have
Is it PE? I mean, this is Euclidean.
yeah, it is Euclidean, but
It's
that
very
no, I don't think that is the issue. Her question is that why am I not having something like a 2 omega p? Right? When you do Euclidean 3p, you put 2 omega p. So when I do Euclidean 4p, why am I not putting a 2 omega p of the 4p? Right? That was the question. Then you don't need, because the Euclidean 3p is not invariant under the 4-dimensional O4 group or a Lorentz group. Therefore, you needed an 1 over 2 omega p to make
That's
it.
what I was saying. Anyway,
Yeah, that is right. While here, what we are doing is that actually this is Lorentz invariant. Whether in Euclidean or in Lorentzian, if I had taken even an I out here, this will be Lorentzian. Okay? So that is not what we are doing. Okay. So your point is can be a source of confusion. We have done this for non-relativistic propagators several times, or even relativistic propagators using 3-dimensional x and 3-dimensional y. Then I introduce a 3-dimensional p, which is a complete set of states. Then the integration measure will have an 1 over 2 omega p. What we are doing here is something different, and it is very interesting in that sense, that as I explained to you, you can think of the relativistic particles which are moving in 4-dimensional space with the time being attributed to its own proper time. That is what we are doing. These propagators are in a 4+1 quantum mechanics, so to speak. Okay, fine. So we have got this, and we want to evaluate this. I mean, this is now straightforward. Once you have got up to this point, I just need to keep one of them. Yeah, okay. I'll keep this. Okay, so we will do that. Having gone up to this point, I can just integrate over that ds. So now I take that integral ds over as e to the minus s. Okay, that integration gives me logarithm with a minus sign. That is how it originally came from. So this will become half. If signs are wrong, you can correct it later on. d4p over 2 pi to the power 4 log p square plus m square. Just to be very precise, let me put PE here. This is what Rajiv was pointing out. That is all Euclidean. Okay, so it's a Euclidean 4 momentum and all. So good, we have got another infinity. And of course, manifestly divergence, a log p square integrated over p4. But this has an enormously simple physical meaning. That is what I wanted to show you. So you have got this. Now, how do we extract the physical meaning? Every manipulation from now onwards is illegal, but it will get you something very interesting. So we will do that. That is the reason we do illegal things anyway. So this is upon m square. You take the derivative of this quantity with respect to m square, because then we just want to bring down the power. So this will be half integral d4pe over 2 pi to the power 4. This will give me 1 over p Euclidean square, which I am going to write p naught square plus omega p square. So let us make sure you understand the notation. I am differentiating it with respect to m square. Derivative of the log just brings down 1 upon that factor. It's m square itself, so there is nothing further to be done. Then pe square I am going to write. This is Euclidean 4 momentum. So pe square will be the p0 in the Euclidean space square plus the vector p square, right? The vector p square plus m square is what I would call omega p square. That is the definition of over omega p, is p square plus m square, 3-dimensional vector. So this is what I want to do the integral on. So let me write this as a d3p then I have a dp0 integration. Okay. Now I don't remember this by heart, so I have to work it out. So this will be equal to this integral is dl effective upon dm square is half integral d3p upon 2 pi the whole cube, and I will take 1 over 2 pi into this dp naught over 2 pi minus infinity plus infinity of 1 upon p naught square plus omega p square. So take a omega p square outside. So this is 1 plus. You have an omega p square outside. Then this p naught I am going to divide it by, so this becomes some p naught upon omega p, which I will call x. So p naught upon omega p is what I am calling x. So this p naught will be x and an omega p, so 1 over omega p comes out. Okay, so this is going to become integral over dx 1 upon 1 plus x square, which is tan inverse of x, evaluated between minus and plus infinity will give me a pi. So I get a pi, which will just go away with this. And I get 1 upon 2 omega p. So this is 1 upon 2 square root of p square plus m square. This is dl upon dm square, so integrate again. So L effective is half integral d3p over 2 pi the whole cube, half something to the minus half integrated over itself, so that is plus half, so that takes away this half and you get omega. Now is a good time to put this half inside and also write a h cross. So this is that beautiful result which I told you long back. What it tells you is that this L effective which we have computed here is just again sum of the 0 point energies of all the harmonic oscillators. Of course, except that we don't see any harmonic oscillators yet in the whole picture. Okay? It is slightly less alarming or mysterious here because we are working with a field and the field has a D operator acting on it. So we know that there are harmonic oscillators there, because if you decompose that field into harmonic oscillator, it's very natural. So that is what you are going to get. But as I said, this is divergent, that expression is also divergent, but the divergences are of that kind that it exactly matches. So what does it mean? What is that this quantity, the physical meaning of this? So further you go back to this. We want to substitute this here. So let me call this entire thing as some E naught. Okay, it's an integral over momentum of this energy. So it's some kind of an energy density which I will call E naught.
There'll be a negative sign with this, I guess.
I don't think there is a negative sign. Why should there be?
Because L effective is normally written with minus h.
No, I haven't come to that. I'm still working in the Euclidean. That will take care of itself. Okay. So let me just okay, you are saying that I should have defined this with minus E naught, which I am not doing here because I just want to have a notation for this E naught, and then we will plug it in and see what happens. Okay. So now we go back and write it down in that expression. So what we find is that this determinant of d to the minus half, which was sitting here, okay, so when you do that integral, that is the left hand side, that is integral over d phi e to the I a plus I integral j phi dx, which is the left hand side, what you get is your determinant of d to the minus half, which is exactly what we have called this quantity. It is exponential minus integral d4 of x Euclidean times this E naught, then it is multiplied by a factor which is nothing but our 0 plus 0 minus in the presence of J. Now let us go back. What is d4xe? d4xe is dte d3x, and our substitution rule is it is equal to te, right? So this dte has an I dt, so this is I d4 of x. This is fine because this is e to the minus I dt d3x. Let me just write this out separately. dt d3x of this quantity. I told you that this is energy density because this has dimensions of energy. d3p is 1 over L cube. So this is energy density. Integrated over d3x, it is going to give you the total energy. So this is e to the minus I integral dt of some energy. Now again, those people who have done the assignment would have noticed that when we worked out originally this quantity for two sources, and when we computed the limit for static sources, we got almost similar expression, in fact identical expression. It was e to the minus I integral over dt of an energy, and that energy there turned out to be the Yukawa interaction potential energy. Okay. Here what we are getting is that this again has a phase, and that phase is contributed by the 0 point energies of the system. So normally when you look at the transition amplitude because of this in the presence of a source, you just compute this quantity, you don't care about the phase. But I just thought that I will show you that that phase is not some completely unknown quantity, but it has a very simple physical meaning. It is contributed by the sum of all the 0 point energies of the state, which is what you would have expected, because if I had done this whole thing in Schrodinger picture, every one of the oscillators in the ground state would have got e to the minus I integral over dt of half h cross omega, and when I multiply all the oscillators together, then e to the minus I half h cross omegas will add up, and that is what will give you this, and that is your total energy. Okay. So the determinant of d which we work out has the meaning as the ground state energy of the system. Now suppose you have a field and you put this field in an electromagnetic field, in an external electromagnetic field. We don't even know how to do this yet because I haven't taught you the field, I haven't taught you how it couples to electromagnetism, all that we will do. So if you do that, and suppose you compute the same quantity again, then what you will get is the ground state energy modified by the presence of an electromagnetic field. So if the loops which I wrote down, these loops are the vacuum loops of the particles or the vacuum fluctuations of the field which is residing in the externally specified electromagnetic field, and these vacuum fluctuations get disturbed by the presence of this external field, and the moment it gets disturbed, this E naught will change. This E naught can change in two ways. First, right now it is real, I mean it may be divergent and all that, but mercifully it is real. It can become complex. If it becomes complex, then the vacuum to vacuum amplitude will take part of it into it, and it will start showing that the particles can be produced from the vacuum, and the vacuum is not stable. Vacuum will decay. The second thing which will happen is that it will have a E naught which is a real E naught, but it depends on the external field. So if you do this, when you are doing this kind of action, there will be extra terms due to that electromagnetic field which you have thrown in, which you are not studying in this. So this E naught will go and add to that. Therefore, it will back react on that electromagnetic field, and you can ask how much that back reaction is. After all, if it is producing particles, it should have a reaction back as well, and you can compute these things out. So this technique of evaluating that determinant, if you can evaluate that determinant, then there is an effective Lagrangian out of that determinant, and that effective Lagrangian has this interpretation is extremely general, because we never use the form of this D until we wrote down the answer as this log. At the level of e to the minus s dxx, we don't care what that d is. If there is a phi d phi, whatever that d depends on, you will get a result here. Here, of course, it is trivial because it only depends on m square, and m square is some constant, so you don't gain much out of it. But in other cases, we will find that it is going to be much more useful. Okay, fine. So that's a good place to stop. What we are going to do next, I mean, let me just change gears here so that next lecture tomorrow I can start afresh. We started from a relativistic particle, evaluated its path integral, found as xy. Then we showed that in Fourier space that can be interpreted in terms of a whole lot of harmonic oscillators, and there is a field which can be constructed out of this harmonic oscillator. Then we said, okay, the moment you have harmonic oscillators and creation and annihilation operators, it creates particles and kills particles. Therefore, let us take that as the starting point. We said, let there be a source which can create particles and destroy particles, and ask what is the amplitude for the vacuum to remain a vacuum under the action of all this. Then we found an expression for that. Then we said, if I do a Fourier transform of that, I again get the fields. The original fields which we got in terms of harmonic oscillators, and then wrote down the action for the harmonic oscillator. Converting it, we got an action for the field. Here we do the Fourier transform of this, and we got an action for the field. So it sort of tells you that whichever way you go around doing this, you are going to be stuck with a bunch of fields. So this is the starting point in all the textbooks. What the textbooks would do is, let us start with a field theory. Let us start with a classical field theory and see whether I can quantize it. Okay. So our next approach would be to start with the action functionals for different kinds of fields and ask how can I quantize that and obtain the particles out of it. This is a very general and very powerful method, and in fact if you want to introduce interaction, this is the fastest route, which is what we will do. But in order to do that, okay, there are 2 points. One is purely mathematical, the other is a bit conceptual. The mathematical point is that you want to understand what these action principles are at a classical level. And then you have to come up with rules for quantizing them. Now, in the most elementary context which you would study, like scalar fields or complex scalar fields, these are trivial. I mean, it was sort of fun. The place where we really need it is for electromagnetic field. Because if there was one field which was really a field which we wanted to quantize and get particles out of, that is electromagnetic. Of course, there is also gravity, but as I said, we don't understand gravity, so we can't do this. So you have only one classical field in your hand, which is the electromagnetic field, if you leave out condensed matter physics. So this electromagnetic field, when you try to quantize, you find that you run into some problems. In the sense that it is not very straightforward. There are issues related to gauge invariance, etc. So you have to understand the structure of the classical theory very well before you can do the quantum theory. So the next few lectures, I will introduce classical field theory and introduce all the structures which you need for real scalar field, complex scalar field, and electromagnetic field, and their coupling. And then we will come back to quantizing each one of them separately. Now, the conceptual point is the following. Are these fields real? Do they exist? This is a tricky issue because the way I have approached the problem, ultimately you want to calculate an amplitude for a physical process. Okay? So here we took the amplitude for a vacuum to remain a vacuum in the presence of a source. You can take two particles, scatter them off, and ask what is the scattering amplitude. These are very well defined questions. It can be done experimentally. But the other question which you would ask is, suppose you have a field configuration and it has some amount of energy. Can I use it? Now, this answer is not completely known, and there are different shades of opinion. I would prefer to take the point of view that fields are convenient tools to compute numbers which can be checked against experiment. Because the reason is that already we have encountered quite a few infinities, and all these infinities arise because you are going to work with a description where you assume that your description is valid all the way to zero separation between the points. I mean, that is where all our divergences originated, okay, mainly. Now, if you do condensed matter physics and you think of the sound waves as a field, classical field, because the lattice vibrations can be written down in terms of wave equations and there is a field, and then you quantize it and you get your phonon. No good condensed matter physics will ever say that it exists all the way down to zero separation, because there is a lattice, and at that lattice separation things has to break down. There is no continuum field theory there. Is there a lattice separation in our real space-time? We don't know the answer to that. Therefore, whether the field is something which can be defined all the way down to the lowest energies is not clear. It is closely related to the fact that if you have a field theory and you say that I am looking at separations which are going to zero, you are talking about energies which are infinite. Do we know what is happening at infinite energies? Again, clearly the answer is no. Our experimental probes probe up to some energy at any given time. So the correct philosophy to adopt in the entire field theory is something known as renormalization group. It's a great contribution by Ken Wilson and many others, and it came from condensed matter physics. And in fact, in condensed matter physics, whether you need it or not, in field theory you definitely need it as an interpretational tool. So what is done there is that you want to work in a field theory in an energy range from E1 to E2. E1 can be 0, E2 is some highest energy level. Then you say that the physics beyond that energy level should not affect the physics below this energy level, except through certain finite set of numbers, okay, which are called the coupling constants of the theory. When you write down the Lagrangian, there is an m square. Now the m square of an electron, is it the same at all energy scales? So in order to understand that, think of the effective mass of an electron in a crystal lattice. All of you have done this in solid state physics. The effective mass of an electron in a crystal lattice is different from the effective mass outside. That is because you can take the electron out of a crystal lattice, put it outside and measure it. You can measure both. But if the electron is coupled to electromagnetic field, what is the mass of the electron when it is not coupled to the electromagnetic field? This is not an experimentally well-defined question, because you cannot do this. But in principle, the physics beyond a particular energy level, which you are integrating out, is going to affect the low energy physics only in terms of the constants which appear in the Lagrangian. So the entire philosophy I will take is that the fields which we are going to introduce are tools to work out numbers, and they have a finite domain of validity. Even though formally we will be doing integrals over like this d4p integral all the way to infinity. Just see here, the divergence came because we are integrating this d4p all the way to infinity. So we don't know what the field theory which we started out with, the box phi is equal to m square phi, we don't even know whether it is valid at very high energies. So these kinds of things would be interpreted by saying that all field theories which we are going to talk about are effective field theories below a particular energy level, and then everything is fine. We can work with that, we can calculate things and then compare them with experiment, and we can also ask how these things are going to change when your effective field theory cutoff stage is changed. This is the philosophy with which we will approach field theory from the next lecture onwards. Questions, comments?
So I have a question about something that probably you mentioned later.
Right.
So this effective action
Right.
and the Wilsonian effective action, they
They are essentially the same.
how come? I mean, because
Yeah, it
there was
will.
any connection.
Okay, so the way it will work is that when mathematically you do this, you think of a field as divided into, let us say, slow modes and fast modes.
Right.
So you take the same field and you divide them into slow modes and fast modes, which is like taking the Fourier space and cutting it off at some momentum scale. So higher momentum are fast modes and the lower momentum are slow modes. Then you write down your Lagrangian. Then the slow modes will couple to the fast modes. Then you integrate out the fast modes. Then you will get a low energy effective action for the slow modes. This is the Wilsonian effective action.
Right. But I don't see why that is the same as this.
That is exactly what we have done, right? We have integrated out phi. Think of this phi as the fast modes, and then this d will have the slow modes. Of course, the structure of the effective action, log, etc., are very specifically dependent on that operator being just box plus m square. That certainly will change. You will have a general operator, but integral ds over s e to the minus sd evaluated between the two. That is a generic prescription. And in fact, we will work it out. We will be doing it for lambda phi 4 theory and electromagnetism, at least two of them. Okay. But philosophically, they are the same. You are integrating out certain degrees of freedom, and its effect is translated into parameters. That's what it is. Anything else? Okay.